Okay, last week we proceeded for section 7.2, which is still the typical transmission line system. And we have a termination of Z sub R as the low of this transmission line system. And in general, we can write up the total voltage and total currents, VD and ID, as a function of position D, And as equation 7.18 shows, it can be divided as the summation of forward-going and reverse-going signal, which can also be known as the incident and reflected signal, V plus and V minus. So V plus and V minus are the incident and reflected signal at the boundary, that is, the voltage at D equal to 0, and so they must abide the boundary condition formed by the termination ZR. So if we write up the boundary condition of the incident and reflected voltage at the low according to the voltage and current ratio, which is the input impedance of the low, we can find the expression for the reflected signal V minus as the product of incident signal V plus and the voltage and the reflection coefficient gamma. So it's remarked as gamma R, which refers to the reflection coefficient at the low location. And as you know, if the low is short, then the reflection coefficient is -1. If the load is an open, then the reflection coefficient is +1. And if the low is the same as the characteristic impedance of the transmission line, then the reflection coefficient will be 0. The next thing is to write up the total voltage, VD, and total currents, ID, in terms of reflection coefficient, gamma R, and the incidence signal, V plus. So we can substitute the V minus signal on the second term of equation 7.21a and b using gamma R. Note that in both the incident and reflect signal term, we have to bear the phase propagation phase difference, which is marked as exponential j beta d and exponential minus j beta d. So if we organize the two terms a little bit, that is, we can write up the we can change. Well, I mean, in this equation, exponential j beta d and exponential minus j beta d are returned by taking the d equal to 0 location as the phase reference. And in this expression, we try to change the phase reference position as the location of D. So it's rewritten as gamma R times exponential minus J 2 times beta D, 2 times. So because now you are having the location D as the phase reference, so the total propagation phase delay will be 2 times D, the round trip of forward going and reverse going paths. So in equation 7.22, we can replace the reflection coefficient at the load and rewrite it as the reflection coefficient at position D. The magnitude will be the same as the reflection coefficient at the low. So once the termination is determined, the magnitude of reflection coefficient is a fixed number. It's a fixed number. However, the phase of the reflection coefficient, as marked on 7.23b, is a location-dependent function. So as you can see here, it's written as theta minus 2 times beta d. 2 times beta d, as we discussed earlier, is the phase delay of the forward and reverse going round trip. What is the significance of theta? What is the meaning of theta? That is the phase of the reflection coefficient at the load. If the termination is an open, then theta equals to what? Theta equals to 0 degree. If the termination is short, then you will have a reflection coefficient of 180 degree. On the other hand, for any other terminations, including reactive ones, which are the termination with inductance or capacitance, then the angle theta will be a number between 0 and 360, or 0 between plus and minus pi. So a number different from 0 and 180 degree. So once the termination is determined, the reflection coefficient magnitude is a fixed number, but the phase will change as our observation point moves. And so with the new expression for the reflection coefficient, that is the reflection coefficient at the position D, the total voltage and total current can be rewritten as this. So here you have V plus exponential J beta D times 1 plus gamma D, 1 plus gamma D, which means the forward going and the reverse going, the incident and the reflective voltage signal. Note that for the current part, the expression becomes 1 minus gamma D, with the rest the same as the voltage, except for the Z sub 0, the characteristic impedance, and the combination of the forward and reverse going part. So here you have a 1 plus gamma D, here you have a 1 minus gamma D. And what is the implication between the two expressions? What I like to say is, suppose that gamma D is a complex number. Suppose, well, which should be the general case. Gamma D is a complex number. So the V total voltage at D and total current at D will have a phase difference. And this phase difference is not a fixed number. And it may be anything between 0 to 360 degrees. Except for two special cases, which can be shown here. The two special cases take place when the voltage or the current reaches maximum or minimum. So when voltage reaches maximum, which means the 1 plus gamma R, well, the gamma R itself is a real number. So when voltage reaches maximum, the current will reach its minimum. And the voltage and current will differ by 180 degrees. Total voltage, the phase between total voltage and total current. And so does the case for voltage reaches minimum and the current reaches maximum. So if we draw the result graphically, like the one shown here, the total voltage and the total current will be blue arrow, which is the sum of incident voltage plus reflected voltage. So the red arrow are incident signal. The black arrows are the reflected signal. So here we suppose the left is total voltage and to the right is total current. So what is the phase difference between total voltage and total current for this specific case? The phase of the total voltage is here, this angle. The angle of the blue arrow and the real number axis. The phase of the total current will be this one. Again, the angle between real axis and the total current. So the difference between total voltage and total current will be the sum of the two angles. In this case, that would be something around 80 degree or 85 degree. But as you can see, if you change the observation point, and I will remind you that the observation point shall move clockwise, like this one indicates. The total voltage will move clockwise. Okay. So, I think I may have addressed something incorrectly. So if the blue arrow, if the black arrow reaches this point, what is the angle for the total voltage? 0 degree. And if the black arrow, the reflected voltage reaches this point, the reflected current, which is also labeled with this black arrow, will reach this point. Then the total current will have zero phase. The phase of the total current will become 0 as well. So the voltage and currents are actually in phase. I'm sorry, actually in phase. Which means they are both real numbers. The voltage and current are both real numbers when either one of them reaches maximum or minimum. Okay, so another thing that I would like to point out here is, because as I already said, the phase delay is the round trip result. So the pattern, the so-called voltage variation pattern and current variation pattern will be in a period of half wavelengths, because the 2 times of half wavelengths will be 1 wavelength. So the locus of the total of the reflected voltage and reflected current will trace this black circle in a period of half a wavelength. And we know that the voltage and current will appear on opposite side of this circle. And the location difference will be a quarter of wavelength, 1/4 个波长, quarter wavelength. All right, and so as the previous slide shows, we can illustrate the total voltage and total currents on the complex plane. And as D increases, the point A, which representing the reflection coefficient of gamma times exponential minus j times 2 times beta d, will move around the circle in a clockwise fashion, clockwise direction. And as I mentioned already, the path, the distance to travel one circle would be half a wavelength, 0.5 lambda. And at this location, which means voltage at the maximum, current at the minimum, or voltage at the minimum, current at the maximum, both the voltage and currents are positive real number, and they will lead to pure real resistance. The impedance, impedance includes resistance and reactance. But if the impedance is a pure real number, then the reactant part is 0, and you will have a resistance only. And the impedance, again, is the ratio of total voltage over total current. So the input impedance will reach pure resistance at voltage minimum or voltage maximum, which come with current maximum and current minimum. So this is something that you should take note with. All right, the third thing about the total voltage and total current variation is that the maximums, the separation distance between voltage maximum or voltage minimum or current maximum, current minimum is half a wavelength. It's a half a wavelength. Then if you track down the total voltage on this circle, which reaches maximum here and reaches minimum here, and you draw the horizontal line as distance, you will find that the interval, the separation distance between maximum and minimum are half a wavelength. So as you track along if you increase d, which repeats itself for every half a wavelength, then the total voltage will go up and down and up and down. The interval is half a wavelength. And is this a sinusoidal pattern? 这是正弦波吗？不是哦，不是哦，它看起来有点像，但实际上不是哈。So it's not a sinusoidal function. Is that a complete standing wave? Is that a complete standing wave? No. Why? Because the voltage minimum didn't reach 0. The voltage minimum is somewhere above 0. So, which means the incident voltage is somewhat larger than the reflected voltage. Then this can be demonstrated with this. The incident voltage is assumed 1. That's the reason why the red arrow is that long. The reflected voltage magnitude, which equals to the size of the black arrow, is smaller than the incident voltage. So that's the reason why you have some minimum total voltage and some maximum total voltage. If the transmission line is terminated with a short or open or pure reactive termination, then the reflected signal magnitude will be the same as the incident signal. Then this blue arrow may reach 0 every half a wavelength. In that case, the patterns will reaches 0. The minimum of the voltage pattern will reach 0, and it can be referred as complete standing wave. Complete standing wave. And in this case, which is more general, that is because the reflection coefficient is between 0 and 1. It's some number between 0 and 1. So this is referred as partial standing wave, not complete standing wave. Okay? Now, so as long as the minimum is not, the voltage minimum is not 0, this is referred as the partial standing wave. Okay? So the criterion for determining is if it is a complete standing wave or not is determined according to the minimum voltage. Okay? So for partial standing wave, from the perspective of energy delivery, partial standing wave means some of the incident power, some of the incident energy is reflected, but a part of the incident energy is delivered to the load. So this is not an ideal case, but some of the energy is delivered. Okay, so so what is the optimal case? What is the perfect case? The perfect case will be that there is no standing wave. No standing wave. V minus is 0 all the time, everywhere. Then, what is the standing wave ratio of match termination? V minus will be 0, V plus is 1, and the minimum voltage observed for the total voltage will be the same as the maximum voltage. So V minus divided by V maximum will be 1. So the standing wave ratio SWR equals to 1 if the termination is a match load. Okay. So which means all the incident power is delivered to the load, and there's no reflected power. So no standing wave. So standing wave if you have a match load. All right. Next, we will examine an example, and in this example, we will examine 3 important parameters, which are first the standing wave ratio. So what is the definition of standing wave ratio? The minimum voltage and the maximum voltage observed on the voltage variation profile of total voltage. Total voltage. The minimum and the ratio of minimum and maximum voltage on the total voltage pattern is the standing wave ratio, which has a standing wave ratio will have a minimum number of 1 if you have a match termination. So what is the worst case? The worst case takes place when the reflected signal is as strong as the incident signal. So you will form a voltage null on the total voltage pattern. Then the V maximum divided by V minimum will be some number divided by 0. Then the standing wave ratio will blow up as infinity. So the standing wave ratio variation range is between 1 and infinity. 1 is the best case you can have, and infinity is the worst case, which means you have a complete standing wave and no energy is delivered to the load. Another significance of the standing wave ratio is the magnitude of the reflection coefficient. Well, if you check up your textbook, you should find out the definition for standing wave ratio in terms of reflection coefficient. I guess it's something like this, right? So if gamma equals to 1, which means total reflection, then you will blow up as infinity. That should be this. Okay. And this equation can be rewritten as the magnitude of reflection coefficient on the left. And there will be some combination of 1 or Q 卡 Q 卡，是 SWR 减1还是加1？哪一个在前面 ？Which one is in the front？ 减1啊 ，OK。Well, so you can show that above equation can be transformed into this one. Yep, all right. So the best case is SWR equals to 1. Then gamma equals to 0. Yep. All right, so the first thing, knowing the standing wave ratio will give you the magnitude of the reflection coefficient. Okay, but you only know half of the answer, the magnitude of the standing wave ratio. So the other half, the half of the property of the termination. The other half of the property of the termination can be known through the second property, which is referred as the first voltage minimum from the load. First voltage minimum from the load. As you remember in the previous slide, the total voltage is shown as the sum of incident voltage and reflected voltage, which the reflected voltage trace a circle like this. And the first voltage minimum, where is the voltage minimum took place? The voltage minimum takes place at this point, right? So what is the implication of the distance of the first voltage minimum? That is, the distance required to move this point all the way to this point. Okay? So this point is the voltage at the load. At the load, at the termination. So as D increases, the total voltage will move to, for this case shown, the total voltage will reach maximum first. Then with another quarter wavelength, it will reach its voltage minimum. Okay? And you shall have D minimum. The subscript minimum is you have the minimum voltage with a number equal or smaller than half an wavelength, because you will reach the minimum in one circle, not greater than one circle. So what is the implication? The implication is then we can determine the angle of the low gamma, the angle of the reflection coefficient gamma. Now, in the first item, the standing wave ratio will tell us the size of gamma. The second criteria, the minimum distance from the load, will tell you the phase, the angle of gamma. Well, you may have one question, that is, why use D minimum? Why not using D maximum? Right? So this angle theta will be the initial phase, will be the difference between the initial phase and the phase of maximum, right? Now, here is the maximum voltage you can have with this transmission line setup. I will say yes, you can do that. But the reason why we are using D minimum instead of D maximum is, if you take another look at this plot, around the voltage minimum, the slope is larger than the slope around voltage maximum, which means it's easier to identify the exact minimum location, which is a little bit difficult to determine the maximum location. Got it? So, yeah, that's the reason behind this definition, which is okay, but anyway, in the textbook we try to determine the phase of the reflection coefficient gamma using the first voltage minimum distance, D minimum. Okay, the third things we can have is the wavelength, that is 2 times of the distance you have the same voltage. That would be the 2 times the distance you have the same voltage. Well, that will be 2 revolutions, because 1 revolution stands for half a wavelength. So with this measurement, by knowing this property, we can know the magnitude and phase as well as the velocity. So we will know the magnitude and phase of the reflection coefficient and what? Vp. The propagation velocity from the third one, the wavelength. Providing that you know the frequency of the signal. Okay, so now let's take a look at the instrument that will be used to do standing wave ratio measurement. This is the illustration. Do we have the real thing? Where you are supposed to, that's the real thing. So, well, it looks a little bit clumsy. So will you have that in the electromagnetic laboratory? 助教回答我一下，你们上那个电磁波实习的时候，是不是有做这个实验？有哈？啊？哦，3个去测嘛，哈，还是老样子嘛，哈，是吧？ So that's a pretty classical one because I have done this lab 30 years ago. Okay, so I have done the same experiment 30 years ago. So in this experiment, you will have what? You will have this, okay? Which is not particularly expensive. So you will have a signal generator that you may be able to tune the frequency. And you will have an oscilloscope. You probably not will be, I'm not sure that if you can have a VSWR meter or not. But to save the cost, you can use oscilloscope to perform this task. And the most important component is this thing. It's the so-called slotted line. It's actually a rectangular waveguide with a slot on it. And you may question that if you have a slot on the rectangular waveguide, will it radiate energy in it? Well, if you cut the slot in the middle of the rectangular waveguide, there will be no radiation because the boundary condition. Because at that point, there will be no horizontal electrical field across the slot, which means if you cut the slot just in the middle, there will be no radiating E and H field. On the other hand, if you cut the slot of the center axis, then you will have some some EM energy radiating from the slot. Okay, but well, you need to go to chapter A to cover the background of this of what I've just said. Okay, go back to the setup. So you have a slotted rectangular waveguide. Therefore, you can put a voltage probe inside the slot to measure the electrical field in the slot, in the waveguide. And the right end of the waveguide is terminated with a short, open, a match load, or anything, okay? Any other kinds of load. You can terminate it with different kinds of load, which may result in standing wave of different size or which are due to different reflection coefficient. So if you move the voltage probe along the slotted line and record, be careful about here, because if you move the probe inside the slotted line, you will observe sinusoidal signal on the oscilloscope. But if you move the slot, if you move the probe along the slot line, you may have a large sinusoidal signal and small sinusoidal signal. So what you need to do is record the maximum of the sinusoidal and put them on this plot at a different position, so that you will end up maximum voltage variation plot like this. So if you only have an oscilloscope, you can still have this result, but it may take you certain amount of time to complete this graph. So here let's check out the important definition. So the first thing, as we already said, is the standing wave ratio, abbreviated as SWR. And we usually use the voltage standing wave ratio, which is abbreviated as VSWR. VSWR. So as you can see here, the definition SWR is 1 plus absolute value of gamma and divided by 1 minus absolute magnitude of gamma. And Of course, we can define the so-called current standing wave ratio, but please ignore this part. Okay? We just use voltage standing wave ratio to prevent from confusing you guys. So, what is the significance of a standing wave ratio? Small SWR. A small SWR means most of the energy is delivered to the load, is delivered to the termination. Therefore, from the perspective of antenna design, if you want to develop a broadband antenna, which means it can radiate signal with a larger frequency range, then you need to show the customer an SWR plot with a large range of small SWR. Here is what kind of antenna it is. Well, it's kind of a variation of dipole antenna, okay? And it's used in the measurement range. 是一般的量测实验室啦 ，measurement range。通常是用在那种电磁相容量测实验室。电磁相容我们称之为 electromagnetic compatibility of electromagnetic interference. And in the past, electromagnetic interference or EMC, electromagnetic compatibility test usually involves lower frequency band. So as you can see from here, for this antenna, the frequency range is from 25 megahertz to approximately 100 megahertz. And the antenna shown here is of certain sizes. What kind of sizes? Can you get an estimation about it? What is the frequency of 100 megahertz signal? Well, it's 3 meters. What is the frequency? What is the wavelength of 30 megahertz? That's 10 meters. And I had mentioned that before, that to produce an antenna of a good radiation frequency, the antenna size must be in the same order of the wavelength, which means the antenna size must be in the order of a few meters. And as you can see here, the size of the antenna is about at the most 1.5 meters. So the SWR is actually not very good because it's a little bit too small. So if you examine the standing wave ratio, it's between, well, the criteria used here is 10, which is a number relatively large, a relatively large number. Usually, we will use VSWR equals to 3 as the criterion for the operation band. Well, that's a commercial product, and for commercial product, you need to show the VSWR spectrum to convince that your customer that your antenna is good at a certain frequency band. All right, the next thing is the distance of the first voltage minimum from the load. As I explained earlier, it's the distance from moving the total voltage to reach its minimum. So if you begins here, you will take the distance will be larger than than a quarter wavelength. However, if you start from here, then the distance will be a smaller value. So according to the value of the D minimum, you can determine the phase, the angle of your reflection coefficient. If you terminate your transmission line with a short, then the D minimum will be what? Will be 180 degrees. Now, if you terminate it with your transmission line with an open, then, I'm sorry, the D minimum will be quarter of wavelength, then theta will be 0. On the other hand, if you terminate it with a short, then D minimum will be 0, and the angle of the reflection coefficient will be minus pi, which is 180 degrees. So the function, the purpose of this measurement is try to derive the angle of the reflection coefficient. Next is the wavelength, which can be found by observing the voltage variation profile. The distance between minimum or maximum will be half a wavelength, as I already mentioned. So for this case, so here's a quick example. Here's a quick example. If the load is 15 minus 20J, and the characteristic impedance of the transmission line is 15 ohm, then the reflection coefficient, which can be found through this process. So in the final, you need to know how to find out this number using your calculator, okay? You need to do that. It will cost you about 15 or 20 points, okay? You need to know how to do that. And as you can see here, it involves some division of complex number. So you need to do the division by first changing them into polar form, okay? So the reflection coefficient can be found as 0.6, and the angle is minus 130 degrees. And using this definition, you can find out the standing wave ratio, which is around 3.9. And the first minimum to the distance to the first voltage minimum can be calculated using formula like this, which is 0.065 lambda, as you can find here. All right, so we will continue next week. 好，我们今天到这边哈。